everybody, welcome to our video featuring the concepts of temperature and heat. So what we're going to do today, by the end of the video, here they are. You should be able to define temperature, define heat. You should understand how temperature is measured on each of these scales, Fahrenheit, Celsius, and Kelvin. And more importantly, you should be able to convert between each of the temperature scales. Okay, so to define temperature, what is it? Well, temperature you can always think of as, how hot or cold something is. But why is something hotter why is one object hotter than another? Well, it goes back to what we learned about kinetic energy, the energy of motion. And as the particles in a object move, they have a certain amount of kinetic energy. If they are moving quickly and faster relative to another body, we would say that that temperature is higher. So really, the definition of temperature is the average kinetic energy of the atoms or molecules in a substance. They're proportional to each other. So as the kinetic energy increases, so does the temperature. As the kinetic energy decreases, the temperature goes down. And this is just a way for you to think about it. We have, these particles of matter here and a warmer object, and my larger arrows are trying to show you that these particles are moving faster. And when they move faster, they collide with each other with more energy than they do in an object that has a lower temperature. The particles do not collide as much. And we see that consequence of that as a decrease in temperature. Okay, so how else we can think about it is when you have a cup of coffee and you touch that cup and the warmth you feel, well, that's actually due to the transfer of kinetic energy from the coffee cup to the surface of your fingers. When you touch something that is cold, you're actually giving energy to that colder object from your hands. So it's this transfer of kinetic energy that we feel as warmth or as the objects being a colder object. Here's another way to think about it. You have an object A, which is the warmer object, and object B, which is the colder object, represented by, that purplish color. And I want you to imagine we put this warm object and this cold object together, and what happens when they come in contact with each other is that the warmer object will will transfer kinetic energy, or transfer, because of their collisions, that kinetic energy is going to be transferred to the colder object. And this is going to go on until both objects have the same temperature, is what we refer to as equilibrium. And we'll get into a little bit more about that in class. So now we can define heat. I want to define heat as the energy that transfers from one object to another because of the difference in temperature, or because of a temperature difference between them. We're going to call that heat. So when we think about heat, don't think of it as a substance, don't think about it as a material, and certainly don't think about it as something that an object has. It's kind of the energy that is in transit or being moved from one object to another. And why is it moving from one object to another? Is because of the kinetic energy that those particles have in that object, the collisions that they undergo. Okay, so you can think about the hand here is transferring energy from the hand to the ice, your hand being warmer, the warmer body, and the ice being the colder body. Okay, so again, let's think of heat as in transit from a warmer body to a colder body, not a substance. Matter contains energy, not heat. Heat is the result of the collisions of molecules in an object. The direction of heat flow is determined by temperature, and our understanding is that we're always going to see heat transferred from a warmer object to a cooler object. Okay, so how do we measure temperature? Well, you know that we measure temperature using a thermometer. And a thermometer is a tube with a liquid in it, and as the tube is heated, the liquid speeds up. The kinetic energy of those particles in the liquid speeds up. The collisions cause the liquid to expand, spread out, takes up more space, and we read that as a greater temperature. The opposite happens when the liquid is cooled. So again, as the temperature increases, the fluid in the thermometer will rise. As the temperature decreases, it will fall. This is directly related to the motion of the particles and kinetic energy. Okay, so now we have these temperature scales. Fahrenheit, which is used in the US, water freezes at 32 degrees Celsius, it boils at 32 degrees Fahrenheit, and boils at 212 degrees Fahrenheit. The Celsius scale is pretty much used everywhere else. Water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. We're assuming that we have a standard temperature and pressure here with these reference points, so we're not decreasing or increasing the pressure over our substance or over water, which we'll get into a little bit more when we talk about gas laws. Okay, so the Kelvin scale is another temperature scale. It's an SI unit, and it has a reference point of absolute zero, and that pretty much means that it can get no colder than absolute zero. The kinetic energy of those particles of matter is zero. Okay, so here are 3 scales side by side. I really like this diagram because it shows you 3 reference points. It shows you absolute zero on all 3 scales. It shows you where water freezes on all 3 scales, and it shows you where water boils on all 3 scales. So let's take a look at the Fahrenheit scale. Water freezes at 32 degrees Fahrenheit, and it boils at 212 degrees Fahrenheit. So there's a distance of 180 Fahrenheit degrees between where water freezes and water boils. When we look at the Celsius scale and the Kelvin scale, what's really cool here is that water freezes at 0 degrees Celsius, water freezes at 273 Kelvin, and the distance between where water freezes and water boils on both of these scales is equal to 100 units. So in other words, 0 degrees Celsius, water freezes on the Celsius scale, 100 degrees Celsius, water boils on the Celsius scale. Water freezes 273 Kelvin, and water boils at 373 Kelvin. So the difference between where water boils and water freezes on both scales is equal to 100 degrees, or simply 100 Kelvin. And really we can conclude there that the quantity of 1 degree Celsius is identical to 1 Kelvin. The only difference between the 2 scales is that they're kind of shifted by 273, so it's really easy to convert between them. So let's take a look at how we do these temperature conversions, and I want to start off with the hardest one first. So what I want to do is go from degrees Fahrenheit to degrees Celsius. Well, when we take a look at the scales, we see really 2 problems. One is that since we have 32 degrees Fahrenheit, the place where water freezes on the Fahrenheit scale, and that's equal to 0 degrees Celsius on the Celsius scale, we see that the scales are offset by 32 degrees. So to make up for that difference, we have to minus 32 degrees Fahrenheit from whatever temperature in Fahrenheit we're given. That solves one problem. Now, if you look closely, we have another problem, and that's the distance between where water freezes and water boils on the Celsius scale is 100 degrees. That same distance, however, takes 180 Fahrenheit degrees. So our Celsius degree is bigger than our Fahrenheit degree. So how do we solve that problem? Well, we simply multiply by a ratio. We take 100 degrees Celsius is equal to 180 degrees Fahrenheit, and we're going to divide those two, and then we're going to multiply that quotient by our degrees Celsius minus degrees Fahrenheit minus 32 degrees Fahrenheit. Now, if you were to simplify 100 divided by 180, you would see that you would get 5 divided by 9, or 5 degrees Celsius divided by 9 degrees Fahrenheit. That's simply the fraction that you're used to seeing for this equation to go from degrees Fahrenheit to degrees Celsius. So that's why we do it. It's the ratio of degrees Celsius to degrees Fahrenheit. And the reason why we have degrees Fahrenheit on the bottom here is so that our degrees Fahrenheit cancel out and we're only left with degrees Celsius. Pretty cool. Okay, so now to go from degrees Celsius to degrees Fahrenheit, well, the same 2 problems exist, but we're just kind of going to invert them, and you can play around with the algebra and see, but I'm just going to give it to you here, which is degrees Celsius is going to be multiplied by a ratio, which is just the inverse of the 5'9" to 9 degrees Fahrenheit divided by 5 degrees Celsius, and we're going to add 32 to it. So you can see where those two equations came from. It's one thing to memorize them, but it's another thing to understand why we're using 5/9 to go from Fahrenheit to degrees Celsius, and why we're using 9/5 to go from degrees Celsius to degrees Fahrenheit. It's the ratio. It's how we solve the problem, the relative size of 1 degree being larger than the other. Okay, easy here, and that was the hard part. So how to convert from degrees Celsius to degrees Kelvin? We simply want to take our degrees Celsius and add 273 to it. That's it. That's all you do to go from degrees Celsius to Kelvin. How to convert from Kelvin to degrees Celsius? Easy. Just take the Kelvin amount that you're given and minus 273 from it. One of the things I remember getting confused, if I would forget, do I add or subtract? What do I do? Just remember that Kelvin can never be negative. So if you're getting a negative number for your Kelvin, then you're probably doing the wrong mathematical operation. Okay. Here are the equations. They probably look more familiar to you because I took the units out, even though it broke my heart, but just so doesn't look as scary. This is what you're used to seeing in math. So this is what, you can use to solve the problems that we're going to do next. So write them down. Pause the video, write them down. Okay, so here we go. What's 12.9 degrees Fahrenheit in degrees Celsius and then in degrees Kelvin? Well, you know that degrees Celsius is equal to the degrees Fahrenheit minus 32 to make up for that offset in the scale multiplied by the ratio of degrees Celsius divided by degrees Fahrenheit, which comes out to 5 divided by 9. You want to go ahead and plug and chug right in there. Remember your order of operations, 12.9 degrees Fahrenheit minus 32 multiplied by 5 divided by 9 comes out to negative 10.6 degrees Celsius. If you didn't get that, go back to your calculator. Make sure you're using it right, following the order of operations. Okay, to go from negative 10.6 degrees Celsius, you simply want to do what? You want to add 273 because that's what those two scales are offset by. And you end up with negative 10.6 plus 273. Another way of thinking about that is 273 minus 10.6. Woohoo! There you go. Kelvin equals 262.5 degrees, 5 Kelvin. Don't say degrees Kelvin because that would be wrong. Okay, so this is an interesting one to do. Negative 40 degrees Celsius, 2 degrees Fahrenheit. You want to make sure you're using the right equation. Make sure that in your ratio, the 5 is in the denominator because therefore your degrees Celsius will cancel out. And you're going to add 32 to make up for the offsetting of the two scales. Okay, so all you're going to do here is plug in negative 40 degrees Celsius for your degrees Celsius, and you're going to remember your order of operations, 9 divided by 5. I think that comes out to about 1.8 multiplied by negative 40 degrees Celsius. Plus 32, you end up with, oh my gosh, we must have done this wrong. We got negative 40 degrees Fahrenheit. What? Well, it just so happens that the Fahrenheit and Celsius scale share a common point of negative 40 degrees. So when you see this one on a test, don't panic because you got the same answer. They share a common point of negative 40 degrees. So I hope this was helpful. I'll see you in class, and okay.